In this video, I would like us to return to the properties of sequences and look at their behavior in relation to convergence. So what kind of convergence criteria can we come up with in terms of these different behaviors that sequences can exhibit? So my first statement is that well, a bounded sequence does not necessarily have to converge, because we have, for example, can think of a sequence that is -1 to the nth power, which alternates between -1 and +1. That doesn't have a limit, but it's a bounded sequence. So just because a sequence is bounded, it doesn't necessarily have to be convergent. On the other hand, and that is my first proposition, if a sequence is convergent, it has to be bounded. Proposition: convergent sequences are bounded. Okay, so it's fairly easy to prove. So let A be a convergent sequence with the limit L. Fix epsilon in the definition of convergence for this sequence to be equal to 1, and find the corresponding index, capital N, such that an minus L, and now I will use this different way of writing this crucial inequality. So an should be between L minus epsilon and L strictly included, between L minus epsilon and L plus epsilon, with epsilon now being equal to 1 for all indices that come after capital N. Okay, so what do we have here? Well, we already can see now that for all terms in the sequence that come after the capital Nth term, they are bounded. They are contained in the strip of L-1 to L+1, and there are only finitely many terms before before this inequality holds. So we only have the first, the second, all the way to the capital Nth term before this inequality takes in place, but before this inequality is becoming important. So what we can say that the sequence then an, all terms in the sequence, well, let me just make a note of what I said. There are only finitely many terms not satisfying this. Namely, well, even these terms could satisfy this inequality, but potentially it could be the case that these terms do not satisfy that inequality. But even if that's not the case, we can say that but then the sequence an is going to be definitely bounded below by either L-1, or if among these numbers there are numbers that are less than L-1, then we just have to take the smallest of these finitely many terms. So but it will definitely be bounded below by the minimum of L-1 and these terms. So we'll just look for the smallest of these values, and that should do the job of being a lower bound. And similarly, an is bounded above by either L plus 1, or if any of these terms are greater than L plus 1, then the greatest of these numbers. So that we take the maximum of these numbers, and that should be a good upper bound for our sequence. So it's both bounded below and above, hence our sequence is bounded. And this concludes the proof. So now we see that convergence will imply that the sequence is bounded. The other direction is not true, as I said at the beginning of this video. Now, what we can say that if a sequence is bounded, so if an is bounded, it has a convergent, it always has a convergent subsequence. So this is a notion that we haven't seen before. It just means that we delete finitely many terms from the sequence, and this way we get a new sequence, which is just a subsequence of the previous one. So a bounded sequence always has a convergent subsequence in it, and this is not at all a trivial result. This is the so-called Bolzano-Weierstrass theorem. Okay, we are not going to prove this theorem, it's a bit beyond the scope of our module, but you should know that even though boundedness won't imply convergence, it will imply that there will be a subsequence which is convergent. Okay, so now we roughly understand what's the relationship between boundedness and convergence. And finally, if we want to have convergence, we have to combine the boundedness property with monotonicity. Okay, so this is our final statement for this video. Finally, combining boundedness with monotonicity will imply yields convergence, leads to convergence. Okay, and the statement here is the monotone convergence theorem. Which is a very important result that we will use later on in the module on several occasions. Unfortunately, this theorem, the proof of this theorem, is also outside of the scope of our module, unfortunately. But it states that every monotonic bounded sequence is convergent. In fact, it can be broken into two parts. One can say that a sequence, well, let me just say it rather than writing this. Every increasing sequence that has an upper bound that is bounded above will be convergent, and similarly every sequence that is decreasing but has a lower bound, is bounded below, will also have a limit, so it's also convergent. Okay, I hope you enjoyed this video, and I'll see you in the next one.